Hi, my name is Ming Yao, and this is my third video on hemolysis on the FDA nozzle. In this video, we'll be using ANSYS CFD because we're going to actually be calculating the hemolysis values. ANSYS CFD is a very powerful set of tools that lets you solve virtually any problem in computational fluid dynamics. So here I'm loading up the model, and let's make a few small changes to it to prepare for a further on analysis. So a powerful part of ANSYS workbench environment is the ability to parameterize almost every part of the simulation. Here we're going to define a parameter to define the size of my nozzle. And we're going to also create a nozzle on the other side. By creating parameters, we are able to do design optimization and sensitivity study on our geometry. So this is my main nozzle, and this one will be nozzle 2. Now we're ready to set up the simulation. So we've loaded the geometry into the meshing tool. The meshing tool is physics aware, so it knows that we're trying to do a CFD mesh for the solver CFX. All we need to do is define the standard mesh will be a tetrahedral element mesh. That should be a hex mesh here, but we have many different hex meshing algorithms. Instead of the standard sweep method, I'm going to use our multi-zone method. And with the multi-zone method, I will be assigning some boundary layer resolution. As we know, hemolysis is dependent on fluid dynamic shear. The shear is most prominent near wall regions. Switch to millimeters here. So we want to ensure that the near wall region is modeled accurately using boundary layer elements, and we want to also ensure that we use turbulence method that allows us to resolve down to the boundary layer. We have various other methods of specifying the boundary layer. You can choose to do total thickness or first layer thickness on this model. So let's go ahead and set up the simulation now. First, we want to, this is our project tree here. We're going to be defining our analysis based on this. Start by putting a new material. Non-Newtonian blood is not provided out of the box. So we're going to add a new material, call it non-Newtonian blood. It's a liquid that has a density of 1056. We want to specify heat capacity, 3000 here, and we need to specify a transportation property for dynamic viscosity. We're going to be using a non-Newtonian model. There's a number of non-Newtonian models provided. We're going to be using the Caisson model. In this model, we'll put in some rough numbers. So 20 millipascals, this consistently 3.5 centipose, and we'll do a minimum shear strain rate of 5. So this defines the non-Newtonian behavior of the flow inside of our domain. Then we can go ahead and set up our domain. This will be a non-Newtonian fluid, reference pressure 1 atmosphere, no buoyancy, stationary domain. Our fluid will be using the shear stress transport model, which allows us to model turbulence down to the wall. It even allows you to predict for the transitional turbulence behavior. We need a few boundary conditions. The first will be an inlet boundary. This is right here. And instead of normal speed, we'll put in Cartesian velocity components. We're going to put in a fully developed flow profile, just like we did in the AIM example. So in a fully developed pipe flow, the axial velocity is 2 times the average velocity, 3222 meters per second, multiplied by 1 minus x squared plus y squared. So that's the radius divided by 6 millimeters. Okay. Looks like I made a mistake here. Oh, I need to square it. That's why. So the quick check for the expressions you type in allows you to quickly understand if you made any mistakes or not. That's the inlet. The only other boundary condition we need is the outlet. And that's right here. And we'll give it a 0 average pressure. So now we want to go do the hemolysis calculations. Hemolysis is calculated using an additional variable. The way additional variable works is that we can start with a variable unrelated to the standard Navier-Stokes equation. This variable will get convected down, transported down along with the flow. If we put a source term that calculates the increase of damage to the flow, then that gets included in the analysis. So this will be, we call it the Hemolysis Index prime. There will be a volume value, no units, and a scalar. The hemolysis model we're using is based on, there are many papers, but one of my colleagues, Dr. Mark Horner, has worked with the FDA to characterize some of this. So there's a nice paper with a few different hemolysis equations. Typically, these equations have some sort of constant in the front. Then there's the time, duration raised to an exponent, and the shear stress raised to another exponent. So we want to include all of this in our hemolysis model. It takes a little bit of work. The main thing here is that in our transport equation, we increment the damage with respect to time, not time to an exponent. So in order to clear up the exponent, we need to take some exponent on both sides of the equation to make it all work. So let's go ahead and get started. The first thing to set up is we need an expression for the shear stress. Shear stress is the shear strain rate. So if we right click on the expressions area, we can get all of the variables times the dynamic viscosity times 1 meter second squared per kilogram. This then calculates the stress. Now we want to include our additional parameter as a part of the simulation in this domain. So we just need to check that and ensure that it's being transported using the transport equations. And finally, we want to add a subdomain, which will be our source term for our hemolysis index. So the source will be based on the hemolysis equations, but it's 3.62 e to the minus 5 to the power of 1 over 0.785 times shear stress to the power of 2.416 divided by 0.785 times 1 second to the minus 1. Oh. Looks like maybe I defined the typed the word dynamic viscosity wrong here. And And when it's a recognized value, it should have turned into this italicized value, but we can find our variable for dynamic viscosity. There we go. And I left out a closing bracket here. Okay, now my equation is correct. So here it's saying that my inlet does not have an initial value for my hemolysis prime value, so I'm going to set that to 0. And we're ready for analysis. We can do a couple of things that's fairly standard in CFD. First, we want to define a monitor. So we want to be able to monitor the hemolysis value at the exit, because we want that to stabilize over time. So we're going to do a mass flow average of the variable hemolysis. HI prime here at the outlet. Okay, so this will monitor this value as we go through the simulation to ensure that it stabilizes to the appropriate. Okay, so go back to the Workbench project page and let's run this analysis. Run it on 3 cores locally. You can also run it on clusters, which will certainly make this a much faster simulation. Okay, the simulation is completed. Normally, our criteria is 4 orders of magnitude reduction in the residual. You can see we've gone much further, mostly because our additional variables have dropped to a less extent. But you can see that the hemolysis index is still dropping here. Okay, coming back to the simulation here, we want to extend the number of iterations to convergence to 1,000. And let's go ahead and run the simulation. We'll run this on 3 cores. And here we have the convergence plot for the momentum, turbulence, wall scale, our additional variables, and user points. We want all of this data to drop below to 10 to the minus 4. You can see additional variables are fairly slow, but the momentum and mass should drop down fairly quickly. So at this point, the convergence plot for mass and momentum looks good. The additional variables are still very high, and my user point is dropping quite rapidly, but not fast enough. So we can speed up the simulation by adjusting the speed of how aggressive we are with the time stepping. This is a pseudo-transient methodology for getting a converged solution. Go to time scale factor. Because the mass momentum has so stabilized so nicely, I'm going to increase the speed of this by 10 times. Okay, the simulation has been completed. Let's take a look at the results. So here we have a plot of the hemolysis values on the coupling. We can see where hemolysis picks up as it goes through a thin tube nozzle and then increases as it goes over here. We can also take a look at the velocity. It shows us our jet as the flow moves through the nozzle. And finally, let's take a look at dynamic viscosity. The viscosity of the flow as it moves through the pipe. We can calculate the total hemolysis value, the average hemolysis of the outlet. So going to the expression here, I have a couple of options. We can use the calculator. So this will be a function calculator. We want a mass flow average at the outlet of the hemolysis index prime. And that's this value. And show the expression. And we can do an expression, create a new expression called this is the hemolysis index at outlet to the power of 0.785. And that's our final hemolysis value, the mass average flow of the fluid and how much hemolysis is happening. So this is a quick demonstration of how ANSYS can calculate hemolysis. When we define expressions like this, we can turn these into parameters. So the hemolysis value could be a parameter. I can calculate velocity. So I can, for example, do a maximum velocity, maximum value of velocity in the domain. That could be a parameter. Just like we can define output parameters, I can also define some input parameters. For example, my inlet right now is based on an expression. And this has an average velocity of 0.322 meters per second. So we can investigate how changing, so this will be my inlet velocity average. So we can look at how changing the inlet velocity, turn this into parameter, affect all of my other results. I just need to change this value here to be a function of the inlet velocity. Okay. Now that we have both input and output parameters, one more thing, I want to speed up the simulation so it doesn't take quite as long. When ANSYS reruns the simulation, it'll use the initial conditions, so hopefully it won't differ greatly. Let's look at some possible changes and how that affects our results. We have three main parameters: the main nozzle length, the secondary nozzle length, and the average inlet velocity. So let's do this from 0.3 to 0.4, so that's about a 30% change range. So let's go to 15 to 20, 25, 20 to 30. And we can change this nozzle from about 5 to 10. So here we'll do a design of experiment. And let's run the analysis. After some time, our hemolysis simulation design of experiment has finished. ANSYS run 15 simulations with different geometry sizes as well as flow velocities, average flow velocities. And for each design variation, we have the hemolysis index as well as maximum velocity as output parameters. From there, we can go on to a response surface analysis. This will interpolate our data and fit equations to all of the different parameters and allow us to understand our design and interactions much better. We're generating a sensitivity plot. We can look at the response of different parameters to each other. And the key of a response surface analysis is that we generate these equations that interpolates across multiple variables. The last step here is to generate an optimization study. Here I'm going to try to minimize the hemolysis index while maximizing the average velocity. These are opposing criteria, so we get a series of trade-offs. So these are the final candidates. We can have high inlet velocity and different numbers for hemolysis index. Trade-off plots like these are nice. We have a velocity versus hemolysis index plot. If I need to ensure that the hemolysis index stays below a certain value for my nozzle, then I can identify the right inlet velocity, the maximum velocity. This will be a minimum versus maximum velocity. We take a look at the sensitivity plot, which shows that the hemolysis index is primarily dependent on my inlet velocity, and to a much lesser extent, the main nozzle size, and our secondary nozzle size is not very relevant to the problem. We can also take a look at a sample plot, where we can specify a certain criteria for hemolysis index, and then maximize my velocity to try to get as much blood flow through as possible. And here, select the right design for our nozzle, whether it has a large amount of angle for the secondary nozzle or the primary nozzle. So that's the end of our presentation on hemolysis and the FDA nozzle. Thank you for watching.